a little bit weird, right? And so
Yeah.
can you just talk about what processing techniques are required for flexible electronics? How do you kind of defy the odds or do the impossible there?
So there's two pieces we'll talk about. One is the material science, how to create conductive inks. Basically, we're printing. This is an additive manufacturing process where conductive inks are formulated to be used in really.
Hey everyone, welcome to the It's a Material World podcast. I'm your co-host Puneet. David is here with me today. David, I know you have finals week coming up, but then you're about to graduate, so congratulations.
Yes, thank you. Thank you. Yeah, I've already taken my first final.
Oh,
I'll
wow.
have two more next week. So just squeezing this in real fast. It's almost a break from studying. So
It's a grind season, but you're almost there, almost at the finish line. So that's awesome. But yeah, speaking of that brain break, I think Stan, our guest today, also classified this as a brain break for him. He's chief marketing officer at PulseForge, and he just loves talking about flexible electronics as a whole. He has an engineering background that he then transitioned to the marketing side of things to work with customers and relay kind of the technical applications of this technology for other companies. So we actually met Stan at PuzzleX a few weeks ago. So we just wanted to bring him on for a deeper dive into the technology and the material science of it all. Did you have anything in particular that was your favorite part of the episode?
yeah, no, it's really cool just hearing him talk about how they broke down this huge problem into small parts, and none of the parts were trivial, but he was able to take from his past knowledge and build upon it. But he used the word trickery or cleverness a lot, but it's really cool to see how you can take problems, break them down into the material problems themselves, and then think about what we can do as material scientists or engineers to figure out how to overcome those problems using material science. And so he talks a lot about how he was able to trick silver into being actually like buoyant in water, even though it's 10 times heavier, and all these other interesting problems that then create new problems down the road, but we can solve those as well. And so overall, it was really fascinating hearing about how he took just regular metal and was able to print it and then solder it onto a plastic with 100 degrees C lower melting temperature. So just his process and his thought process of how everything works, I thought was extremely unique and a great insight into how real problems are solved in like industry.
Yeah, it exemplifies kind of that advice about the first principles thinking, and working from the fundamentals, knowing your fundamentals. That's imperative. And that's one of his pieces of advice. He had many in this episode, which is awesome. But he was just like, really know, the physics and the chemistry of things, and you can build on that. You can develop that foundation, and then you can work your way up. And this exemplifies kind of what's possible if you do that. And I think one of my favorite aspects of the episode was one of those applications. It's a futuristic application, but it's regarding like 3D bioprinting and printing organs and the incorporation of flexible electronics, almost like functionalizing it onto tissue to be able to measure performance and go from there. And so I thought that was super cool, just seeing how one of a topic we've covered in a previous episode, 3D bioprinting, how flexible electronics can kind of interact in that space, and also biomedical implants on top of how maybe we would originally envision their use with like EKGs on clothing, or like kind of integrated with clothing, or glucose monitoring, things like that. So just from the medical perspective, that it was super fascinating. And if there's anybody else who is interested in those types of applications, then definitely tune into this episode. But yeah, anything else to add, David?
No, just super interesting guy, and he has a lot of passion for it, and it's very clear to see. So just super interesting conversation that we were able to have, and excited for what you get to hear.
Yeah, for sure. Before we get into the episode, feel free to join our free Discord community. The link will be in the description below. And yeah, we have industry chats there. You can ask questions, just interact with a bunch of other MSEs who are super passionate about this field. So without further ado, let's get into it.
Metamaterial Inc. is a developer of high-performance functional materials and nanocomposites. Meta delivers previously unachievable performance across a range of applications by inventing, designing, developing, and manufacturing sustainable, highly functional materials. Meta is a fast-growing company with a positive and committed work culture and a phenomenally talented workforce. Our employees are inspired to do exceptional and innovative work and are proud to contribute to the success of the company, and they are our greatest asset. Meta attracts people from all countries and cultures with over 35 spoken languages represented across all our teams. Meta believes that diversity drives creativity and innovation. With locations in Canada, the United States, the UK, and Greece, Meta is growing and is looking for new talented people to join the team. If you're passionate about doing your best work, making a difference, and having fun while doing it, apply to one of our open positions at metamaterial.com/careers. All right, hello everyone. For today's episode, we're very excited to welcome Stan Farnsworth, current Chief Marketing Officer at PulseForge. Since earning his master's degree in mechanical engineering at the University of Texas at Austin, he has over 20 years of experience in marketing with a special focus on flexible electronic products. Today, he is joining us to discuss these flexible electronics and also how we process them and the unique properties and applications we can get from them. Thank you so much for joining us today, Stan.
Hi, nice to be here. Great to see you again.
Yeah, great to see you too. It's been a few weeks since we met at Puzzle X, and so now we wanted to do like a deep dive since we only got like 5 to 10 minutes with you last time. So just to start out, what is a flexible electronic and how does it differ from traditional electronics in this space?
Sure. When we think about electronics, and Puzzle X was a great event, by the way. That was really great to meet you there, and that was such an inspiring event. And one of the topics that we think about with advanced technologies is that advanced technologies really depend on an ecosystem of related other advanced technologies. Typically, it's usually not just one piece. And Puzzle X was a great example of that. The organizers pulled together a connection of advanced technologies that flexible and printed electronics is certainly a part of that. But flexible and printed electronics itself, when you unpack that, that is also a collection of really advanced technologies. And the idea is to move away from electronics as we know them, which is generally stiff and brittle and often brickish. If we think of advanced electronics, we think of rack-mounted, everything from rack-mounted servers, which are a form factor of brick, and we think of consumer electronics, which are often form factors of bricks, and we think of even in aerospace and automotive transportation, form factors are also often bricks, and so that's really what electronics. When we think of electronics, I think most of us have that kind of association. Now, the functionality of those are incredible and have been advancing fairly miraculously, really. When we think about the progression of the function that these bricks have, it's astounding and is absolutely having an impact in our culture and in our society. And that's another intersection, by the way, which is going to be interesting to unpack at some point as well, is how does technology influence culture and society and vice versa. But flexible electronics, the space that we're in, is bringing together a set of technologies that gets us away from the brick and moves us more into a realm. And I'm getting out my handy samples here to look at. So this is an example of a flexible electronics. This is plastic and very low temperature, very similar to the kind of plastic that's in a water bottle. So this is just PET plastic.
Stan, can you explain it for our audio-only listeners as well, what you're holding in your hand?
So I'm holding up a business card sized piece of plastic, and it has an image, an outline of a leaf fabricated onto this piece of business card sized plastic. It's very flexible, it's thin, it's just the thickness of paper. It's actually thinner than many papers are. And what we've been able to do using our advanced technologies in combination with existing traditional electronics technologies, which is part of it. We don't want to throw the whole thing out and start from scratch. We want to add technologies into this to add functionality. And I'm putting a 9-volt battery across a set of contacts on this piece of plastic, and it's activating LEDs that have been soldered onto the outline of this plastic, of this piece of plastic, of this leaf on this piece of plastic. And in many ways, this seems like a fairly simple, and maybe the complexity is so ingrained in it that we don't even think about it. But really, it should be impossible to make this in many ways. It should be impossible to make this in one sense, because the soldering process itself requires very high temperatures to melt metal. Solder is metal, and we're melting metal at 200 degrees C up to 250 degrees C. So it's not a low temperature solder, but we're doing this on plastic. And the temperature sensitivity of this PET plastic starts at about 80 degrees C. It starts getting really unhappy at about 80, which is only a third of the processing temperature that we need to get to melt the solder. But we're able to do that. And so we're playing games and being very clever and tricky in how we use physics and chemistry in our favor. And the reason we're doing this for flexible electronics is because so many applications for electronics require some sort of motion or curvature or flexing or bending or some dynamic aspect of the form factor that is not a brick. So when we think about medical applications for electronics, sensors on people, whether it's for a glucose test, monitoring, or EKGs, sort of semi-long-term EKGs for people with different health issues. People are not bricks. I don't look like a brick. You look like a brick. Bricks aren't a good choice of a form factor for these. And we've got to find a way to change the form factor and find a way to carry across the incredible performance that electronics today have, that those technologies are really amazing and are extremely complex themselves. But how do we transfer that to materials and processing methods that let us add an additional completely new dimension of form and the applications that will open. So that's what we're doing in printed and flexible electronics, is developing new materials, developing new process conditions, and then working with different kinds of companies, and also very mindful of societal circumstances around what kinds of products and applications are a great fit, and a convergence for all of these pieces to come together.
Yeah, so I think we'll get to that trickery you're talking about, because it really is amazing. When we met him, I got to hold it, and it's this really thin piece of plastic that can really do it all. So I think we'll get to the trickery of how you're actually able to do that. But I think something that's going to be interesting for our listeners is, how did you get to where you are today? And so, like we said in the intro, you were a master's student, and then you just told us you went to applied materials. How did you get from there to chief marketing officer of PulseForge?
So I that's a fun, to myself as well. It's a funny progression. It all makes sense. There's no discontinuities in this narrative, but there are some assumptions of a spherical cow occasionally through this process. And so I was one of these people that grew up playing with Legos and very, how do things work, and very I knew more about planes and cars than I had any right to at a very, very young age, just through self-exploration around that. And so when I got to Rice to do my bachelor's degree in mechanical engineering, and of course, mechanical engineering was the complete no-brainer. A lot of people really have to think about what are they going to study, and for good reason. There's so many interesting topics. But for me, there was no consideration at all. I just immediately knew that was the right fit for me. And I really thought I was going to grow up and design and be involved in jet engines and turbine engines. So clever how air and fuel becomes mechanical power, which becomes motion. Extremely, extremely cool applications and manipulations of energy for that. And the mechanical complexities were extremely captivating to me. And so that's what I did. So I did specialization in heat transfer and fluid mechanics and machine design, and material science is a huge part of all of that. Yep. And I had a chance as an undergraduate living in the Austin area, coming back for the summer to do some summer projects at the University of Texas at their Mach 5 wind tunnel. How cool is that?
Wow.
Designing and building test shapes to understand how nose cone geometries impact shockwave formation and what that does to because it's a compressed, so air is a compressible material, and so there's you can set up these oscillations in how you design the nose cone shapes, and you can play. And so those oscillations, it turns out, really have a pretty big impact on what the heat transfer through and around the shockwave into the structure of the vehicle at that point. So I was messing around with that for one of the faculty members that summer, and then I wound up doing a master's program in his group as well when I graduated from Rice and came back to Austin. Of course, Rice is in Houston, so it's not too far away, but I came back to Austin. And so I was really on a technical track, and I was pretty sure that I was going to design jet engines when I finished that. But during the course of that, as I was going through my master's work, I satisfied that interest. Like, okay, that's enough. All right, I kind of got to a level of understanding around that I thought was interesting enough. And so I was looking at what opportunities I had, and I was fortunate and had some opportunities to go the NASA direction and work on space station development at that time and mission planning and that kind of thing, which had a very high cool factor. And then I also was still interested in cars, automotive, and that seemed interesting. And so I had a couple opportunities to go that path. And I was relating that we had a job fair come through the university for applied materials. And of course, applied materials makes the equipment that makes microchips, and I really didn't have as deep of an understanding of what was really involved in that. But I thought, well, I should at least go check this out, and was not super impressed in the interview process that they had at their facility here. They were just opening. But and so I didn't think too much of it when I finished the sort of the job fair out there. But they had a different takeaway for that, so they called me and wound up with a pretty decent offer. Actually, I thought, well, maybe I need to take a closer look at this. And so I went back out, and this is one tip, right? Is for when you get a job offer, it's totally okay to go back and re-interview from your perspective to understand more about what the opportunity is. And so I met with the hiring manager, got a more involved tour of the facility, and the technologies that are used to make microchips are sky high cool and unbelievably complex. And yet all of the technologies are so front edge, but they all have to work. And there's so much money in that business that even then I was really captivated by how applied materials and the technologies were converging, and the business and the markets and scaling that. And so I took the job there, and it was so incredible. For 3 or 4 years I was there. But my graduate school advisor, bringing it back now to PulseForge, my graduate school advisor over these years, and I left Applied briefly and went back to Houston and had a really interesting job also in material science, very specifically in material science and scaling some materials testing equipment design and production, which was pretty interesting. But my graduate school advisor, Dr. Dennis Wilson, was starting up a company for nanomaterials and to make and scale the production of nanomaterials and nanopowders. And this was very much before nano was cool. I don't know if nano ever has been cool. It kind of is in a way, but this was on the front side of sort of the nano wave. So this was like 1999 timeframe, right? Going back in our Wayback Time Machine already. And so I was working with him on that. He found some investors that were willing to put some money into starting this nanomaterials company. And I thought that technology seemed pretty interesting. And so I agreed to come in and be employee number 1 for this company. And so I came in to run the technology development of how to understand the fabrication of these nanopowders. And that's a whole tech story as well that I could spend a long time talking about. But if anybody is interested in that, they can follow up with you or me, and we'll talk about nanomaterials and nanopowders and startups and entrepreneur and all the stuff. Yeah. And so, but one of the challenges is that we were able to close this really nice round of funding, and we brought in a business team, and we struggled because the business team could not understand the technologies, and they couldn't understand what we were doing and the journey that we were on, which we were still exploring. This was not a set trajectory. We were very much building and going all at the same time, right? Making rocks and then making a trail out of the rocks that we were making, right? So this is really an iterative thing. But also we were still exploring what the right applications for these nanomaterials were. And so we were doing some very tricky things with physics and science to make these materials, and then applying them in some very tricky ways into markets and applications to really get value out of the unique properties that nanomaterials have. And that's what I really learned, that in addition to this technology innovation piece, there's also very much a symbiosis on needing to understand the market application business end around that, which I just had not thought about at all in all sort of my journey up to that point. But here we were hit square in the face with it, and the business team was struggling. These were smart people with a lot of experience, but they just didn't have that technology piece. And so the investors asked if I would move over and help, right, do more work on the business team and just take my technology understanding and some relatability on communications and storytelling and this to help convey what we were doing. Because I had been having to help them, and I said, whoa, time out. I don't know anything about these topics. They said, well, you're doing it. You just don't know that you're doing it yet. So I cultivate that. And I said, okay, let's try it. It was a scary move to make. But that was when I moved over from the technology piece. And you can take the boy out of technology, but you can't take technology out of the boy or something like that. I'm still very much a technologist, but now have just tempered that and grown these dimensions. And that's what we've done through that evolution at Novacentrics with the nanomaterials and applications. And then that led us to electrically conductive inks as an application for those nanomaterials. And that led us also to the PulseForge processing equipment, which is, David, you mentioned some of the trickery. There's some trickery and these things happen, and some cleverness. And what I've come to realize since then, so chief marketing officer, looking at how do all these pieces converge? How do technologies and markets and customers and people and business, how does all this converge into a thing, and what do we do with that, and how are we doing that at Novacentrics and PulseForge? How are we picking markets? How does our team have this understanding? And we've grown, and we have additional smart business people now that do have technology backgrounds, but we're all still learning. And that's this notion of deep tech. And so deep tech, I've come to really appreciate, is that combination of this collection of technologies, often some trickery, and so it's authentic trickery. It's not snake oil, smoke and mirrors trickery. It's very much looking at things from a different perspective to do some really clever and fun problem solving. And so there's this artistic element as well. There's this sort of creative piece that's really fun, and then how we engage markets. And so as a deep tech company, printed and flexible electronics is a primary engagement path for us, but it's not our only one. There's others that we're looking at as well.
That's so cool. That's like such a fascinating story. And it makes sense, from the jump to jump, how you ended up in that marketing role. So I really appreciate you diving into that. But we talked multiple times, you've mentioned this trickery, and I want to explore that in more detail. And so I know previously you mentioned like that 80 degrees Celsius kind of threshold where that processing for PET gets, a little bit weird, right? And so can you just talk about what processing techniques are required for flexible electronics? How do you kind of defy the odds or do the impossible there?
So there's two pieces we'll talk about. One is the material science, how to create conductive inks. Basically, we're printing. This is an additive manufacturing process where conductive inks are formulated to be used in really mostly traditional kinds of print methods. So screen printing, which is the same method that t-shirt shops use. That's very common in t-shirt shops to do screen printing. Inkjetting, which is often used for different kinds of graphical printing. There's a whole litany of different kinds of printing, and there are probably printed and flexible electronics applications that utilize one or more of those print methods in any particular application. So taking metal and formulating it to make an ink that can be printed is itself kind of this miraculous thing. And we think about silver is a really good electrical conductor, and we want to make an ink out of silver. How do we do that? Well, one of the ways of doing that is to convert the silver into a nanoparticle, which means that it's about the size, it's actually smaller than a blood cell. And you get a collection of these nanoparticles and you formulate them into a carrier fluid of some kind. You make like you stir them in. But of course, the challenge is that, first of all, making the particles is hard. That's the whole thing. But then let's talk about how to make an ink out of that. And the challenge comes from silver, which is 10 times denser than water, which means it sinks like a rock because it's actually heavier than most rocks. But yet we're going to make a suspension in water of these silver particles, and it's a neutral suspension, so that if a silver ink looks silvery and you can print with it, and the silver doesn't all crash to the bottom and fall out of the suspension. So that right there is quite a bit of trickery. How do you trick the water to reach neutral buoyancy with the silver? And the way you do that is you understand what sinking and buoyancy is. You have to back out and understand the physics and the science of what is sinking and what is buoyancy, and what other factors and attributes are there between the water or the alcohol or whatever the solvent is that we chose water because it's very innocuous, right? You can breathe it and it's not a problem. Well, I mean, water vapor, you don't want to breathe water, obviously, but it's not a toxicity issue in the lab like a lot of alcohols and other solvents, traditional graphical ink solvents. So our chemists figured out that we could trick the water into thinking that the silver nanoparticles were not these tiny dense rocks, but were actually these semi-luminous, voluminous balloon structures that had a much larger effective volume than just what the core nanoparticle is. And so you do that with these ligands and these chains that sort of stretch out and extend beyond the nanoparticles. And then you also take advantage of different forces that are inherent in the water, different kinds of surface tensions and different kinds of motion, that turbidity, just motion that happens in the water. And so you actually can wind up creating a fairly stable suspension of nanoparticles in water. And that's what we've done. We've done that for other things as well. And so you print the silver. And so there's a whole set of trickery around making the nanoparticles, which is non-trivial. There's this really cool trickery around suspending the nanoparticles. And in fact, I don't even want to call it trickery anymore. Let's call it cleverness, because it is. And so there's this cleverness around suspending the nanoparticles, and we print them down and you say, okay, that's great. And that's sort of the first step of conductive electronics, is to get these particles printed onto plastic or paper or bamboo or whatever it is, that some textiles that people want to use for these applications. But the problem is that all of the chemistry that went into cleverly convincing the water to have neutral buoyancy with the silver nanoparticles now becomes a problem, because all that chemistry is preventing the silver particles from touching each other really well, and they don't get that good electrical connection. So we've got to do some more work and some more cleverness to kick out the chemistry, to kick off the ligands and the coatings and all the different chemistries that are in there, so that the particles can come back into contact with each other. And that's where you can take advantage of the silver. And so it turns out that a really, really good way to do that is thermal energy. So heating up those inks to high enough temperatures to cook off and volatilize and evaporate and break down that chemistry is really it turns out that's the best way to do it. And that gets the highest performing silver particles to particles contact. And so there's this sort of drying chemistry removal step. But that's our first impasse now on these substrates, is that removal process generally takes some kind of temperature, and that's generally a higher temperature than what those substrates like to accommodate. And so plastic and textiles and bamboo, whatever people want to make these electronics on now. And so that's a problem. And so, but undeterred, that space had continued with these really low performance applications. And so there are some fairly low performance RFID tags and fairly low performance early wearables that were coming along around that. And so those were seeing some success, and that was great because that was validating this whole notion of opportunities for printed and flexible electronics. And so we realized that we could actually take a derivative of how we had been making these nanoparticles, which was its own bit of cleverness, and redirect that to power flash lamps, and that we could use flash lamps to apply some cleverness in how we were heating those ink and substrate systems to remove the chemistry. And the trickery, cleverness, is around how we deliver that energy. And so here we come back to what my background was, which was well-versed in many in heat transfer and understanding how energy moves around like that, and realizing that energy, and I'm not one of the inventors, but I was sharp enough to understand really the potential of what the inventors did. And so it was Dr. Kurt Schroeder and Doug Jackson in our team that were really playing the early games with this. And I recognized immediately that there was real merit to what they were doing. And that is playing games with time. So when we heat these materials, they don't we often think of temperature as being an instantaneous kind of a thing, but it's not. There's a time that it takes for the energy to be transferred, for the materials to heat up. It takes time. And what we're doing with the flash lamps is we're putting in so much power so quickly that we're overwhelming the thermal response of those materials. And so we're able to, through this cleverness, heat the inks to very high temperatures to drive off the chemistry without damaging the low temperature substrate. And so we can build what are gradients. So the hot surface is hot, and the volume inside the very thin, paper thin substrate still is not hot yet. It doesn't know that anything's happened. And so we're creating this seeming discontinuity, but it's not. It's just a very sharp gradient in how we're processing materials. So we can trick, and here we'll go back to trick. We can trick the substrate and the paper and the textiles and the plastic to not realize that it's experiencing this event, but the inks are absolutely experiencing this event. And so that's the first step. And then the second step that we did is we figured out that we could apply that same process to melt solder. And so the solder gets hot and melts much faster than the substrates do. And so that's why we're able to melt and reflow solder and sinter conductive inks and do some other things at very high temperatures, but doing that on very low temperature materials, and work with designers and what are the applications around that, work with manufacturers and how to implement these new technologies that are seemingly impossible from sort of a traditional way of looking at the science and physics, but we're coming at it from a different direction, slightly off center, and looking at, and when we do that, if we think about these technologies are blocks and they line up this way and we see a path and maybe a wall, right? But these famous sorts of illusions where if you come off and look at the same block sideways, you can actually walk right between the blocks. It's not a wall at all. It's just from that perspective, it seems like a wall. And that's what we're doing with our science and our physics and our chemistry and our materials work, is looking at things a little bit off center and finding out that, oh, there's quite a bit of room actually to be clever in how we manipulate these to get to some kind of result that seems impossible from another perspective.
And so for this technology of this instantaneous heating almost, how efficient is it? Like, do you lose a lot of energy to air just because you're trying to hit it with as much energy as possible? And to what resolution can you heat a certain area without affecting the entire substrate?
The really happy news in this, there are many happy checks in this story, is that because we are so targeted in how we deliver the energy and it's so fast, there is not really any collateral heating. So we're not heating the walls of anything. We're not heating the chamber. We're not heating the volume. We're not heating all the stuff. We're just heating that initial material. So on the product side, that's a very, very happy story, because it turns out that, for example, with electronics manufacturing, normal solder reflow ovens, which a normal soldering process will take 5 or 10 or 30 minutes, depending, and our solder process takes half a second, or maybe a second if we need to slow it down for some reason. And it's such a different time scale that we're not heating up all of the other rests, all the rest of the electronics. We're not heating the walls of the system. Now, there is still some heating because of the electronics and some of this, and so we do have cooling inside our system. So it is not 100% efficient, but in a lot of use cases, this technology application can be 80 or 85 or maybe 90% more efficient than a regular soldering process. And considering the regular soldering process is where most of the energy in electronics manufacturing is spent, just because these ovens that are being used, it winds up having a pretty substantial impact. So it is very helpful from a sustainability perspective, because we can now use much more sustainable materials as substrate materials. We can also, our customers can save tremendous energy in their manufacturing process, and so there's a lot of happiness around that use of energy. And from a resolution perspective, the resolution really is limited only by the design. So this is a large area process. We're not using a laser to etch out and expose just a very specific piece. It's a flashlight that covers the whole area. It's on our soldering line, it's a per pulse area is typically 12 inches by 3 inches kind of a range, and we can move a target underneath that and stitch together multiple flashes of the light energy, depending on what the right way is to build that temperature profile, that gradient through the materials. And we can control what those pulse conditions are to a very fine degree. So it's really not limited. The resolution is really not limited in the thermal processing. It's really in the circuit design, the product design, the deposition, the printing methods that are used. And we work very closely with our customers to help them understand what the combination of these technologies can look like. And we help them on the inks piece, we help them on the printing piece. We absolutely can help them for sure on this soldering, sintering, thermal processing piece. And so that's where we come back again to this collection of technologies and the psychology of this, which is another one of these convergence points that's so important for deep tech, which is so often really neglected, is the relationship aspect. And so particularly in the early days of implementing and exploring and implementing how these technologies can impact a particular product space, there's a lot of conversations with all the different people in all the different aspects of the technology and the product and the business and the market, and all these pieces all have to come together. And so it's very relational. And we tend sometimes to think that technology implementations are not relational. And it's very true that at a certain stage in a technology implementation cycle, once the technology is accepted and it becomes semi-commoditized, then the relational aspects can dial down. Then it really does become about procurement and numbers and cost and price and availability. But in the early days, where the technologies are being assessed and iterated and the applications are developing, there is very much a relational aspect and a psychological aspect around that on how that works. And we recognize that and work very closely with our customers to help them understand what we're doing and to help them have confidence in what we're doing, typically from a technology credibility perspective. Does it actually work? Can we hit the performance they're looking for? But also the technology support and just helping them feel comfortable around using this and committing to this for their business.
Yeah, that's super fascinating. I've always been interested in that intersection between, very technical, or technologies, and then the marketing side of things, and finding an application for the technologies that you create. And so kind of looking ahead to future application development stages. Is there a potential for wearable or for flexible electronics to be used in biomedical implants? I know we've touched on flexible electronics for wearables, EKGs, glucose monitoring. So I just wanted to see if biomedical implants are ahead, or in order for flexible electronics, and what challenges come with making an impact in that space.
I would say that is one of the frontier intersections in electronics technologies, additive manufacturing, biotech, bioscience, along with societal interest in onboard monitoring of our persons, right? So direct monitoring, either externally through patches and not just a watch that's adjacent, but patches that are in contact with our skin and our bodies in different ways, but then also internally. I think that there are applications to explore around fabricating internal sensors and monitoring, and maybe even proactively providing signal or stimulus in some way, as an into and not just an out of kind of signal response. And the fascinating part about this to me is that the physics and the science that allows us to be very clever in how we get the benefit of modern high performance electronics materials and design and architecture with 50 and 60 years of good work that's gone into that. We're not throwing that out to translate that to a medical patch. We're not throwing that out to translate that to different kinds of really innovative substrates and materials. So what happens if the substrate material, instead of being an organic material, like a passive organic material, like a polymer, this PET plastic, or wood or paper or something like this, it's cellulose and fibers and this and that. But what if the substrate is a functional biological material? What if it's a tissue or a membrane or I don't know what, right? So what is that? And we've done some earlier work that suggests that yes, indeed, the physics still holds true. We can achieve surprising results with processing high temperature materials, inks, or sintering powders into unique shapes, or working with ceramic materials that require high temperatures, but then being clever in how we work with that. But doing that in either in an environment that is adjacent to very low temperature biological materials, or maybe onto with involving high biological materials. And that is a very, very frontier topic right now. And so this also is a convergence of the background that we have in the electronics, the materials, but also work that's happening in additive manufacturing as well. And we are looking at fabricate printing organs and printing ears and printing livers and growing kidney, some of these things that are happening right now, bones, skeletal materials. But what happens, that's all fine and good, but what happens, can we, as we're building that, can we fabricate a sensor as part of that build? And what does that look like? And how do we monitor the performance of that structure, that tissue, that organ, that physical skeletal scaffolding? How do we monitor that either during the build or even during use? And I think that that's a very frontier topic that's very exciting to me to think about. And we do have customers and contacts that we're at the early stages of that intersection now. And I think that the possibilities of that are just so enormous that it's hard even to think about.
I had a question there because you mentioned the potential for printing organs, and I think 3D bioprinting has it's been a topic we've covered previously, and one of the main challenges to kind of making that a reality is like the bio inks and finding a material that can emulate like vasculature, right? But then also, have all the required material properties and not be toxic to the human body. And so I was just wondering, from the flexible electronic space, how do the materials that are commonly used there interact with the human body? Is there any potential challenges from the toxicology point of view?
So it's very possible to engineer on the electronic side to use materials that are not toxic at the sorts of volumes and weights and amounts that would be used in these applications. So this was a decision that we made very early on at Novacentrix, going back to that earlier topic around, well, we can make inks out of all kinds of materials, and we can do a lot of kinds of chemistry to create this cleverness around how we suspend the nanomaterials, and we can pick the carrier fluids that we want to use. We could pick an alcohol or a methyl ethyl ketone or something that's not as happy and not as healthy for our bodies, or we can use water, which of course is often much healthier than methyl ethyl ketone. And so MEK, which is typically used, it's a material that's commonly used, and it's moderated, and people have safe practices around that. But from a person, a use on your person, we have made very conscientiously the decisions at each step of the way to use materials that are less harmful or not harmful at all. And so using water and using some of the surfactants that are completely, if not mostly innocuous, certainly in comparison to other materials which may often be used in these formulation efforts. And so I think that there is hope for that. I think there's obviously still a lot of work to be done there, and the biology is just, I understand the complexities of the inorganic materials that we've done work with the nanomaterials and the chemistries, and on the biology side, to add the complexities of biological interactions and the organic chemistry pieces around that is just mind-numbingly complex. And so we definitely are looking forward to continuing to work and grow in that area, but that is very frontier.
So talking about these frontier technologies, I think we would love to hear what 10 to 20 years looks like in the future. For my own interest, specifically around what does a flexible electronic look like? I know that you're working on like the metals and like basically the motherboard, but what about all the other components that would go into like a more complex machine like batteries and other like memory and stuff like that? How does that look like within the next 10 to 20 years, do you think?
It becomes much more integral and normal of a thing. Right now, flexible printed electronics still has a sort of a novelty panache to it. It sounds a little bit boutiquey and probably expensive, and some of it is, but generally not always, because of the technologies that are being used. And I think that as we look at applications spanning batteries are a great topic. And that's a key application area for us as well. There's some really, really amazing material science technologies that are coming out right now that maybe we'll follow up with at another time as well, that we haven't had a chance to talk about ourselves with you yet, David and Puneet. But there's some really amazing things that are happening that I saw actually as a result of introductions that came out of Puzzle X that were really mind-blowing. And but the future, the technologies will continue to converge. The technologies right now are developed to a fairly high degree. We sometimes think of, you'll hear TRLs, technology readiness level, or MRL for manufacturing readiness level. A lot of these component technologies are relatively mature at this point. They're at TRLs or MRLs of 5 and 6 and 7 and pretty well ready to go, and maybe also already being used in some capacity. But what hasn't happened yet is a lot of the propagation and the growth and the use of those technologies. And the leading edge early adopters are continuing to be the early adopters, and this follows our normal sort of S-curve adoption profile, where the early adopters are early adopters, and then you get the sort of this growth in the number of users, And people that are just now becoming aware of these technologies, when they come visit us and get a tour of what we're doing, we've been doing this for some time and have customers who are doing this, but these new folks are coming in early in this. And so it seems quite mind-blowing to them to see this. And it's a relatively advanced technology and how it's being used. But to them, it seems quite futuristic. And this soldering tool, we've had a couple of engineers come in and say that this looks like something from Star Trek, right? It's fairly well developed and it works really well. And it's got this super cool touch screen user interface, and it's making things that should be impossible, but yet they're happening right here and I can see it. And so that will continue to propagate. And so I think in 10 to 20 years, we'll see a couple things. The technologies that right now are frontier will become more mainstream and widely used. And I'm so excited to be a part of and to see how the frontier, the front edge of this continues to evolve. And I gave a talk at a wearables conference in San Francisco in July, and it was a little bit of a logger format talk. So I had time to go into more of this narrative and on the how this connect together with nanomaterials. And one of the questions, and what happens when I get a chance to throw out more of this, is that the questions really open up at that point. And so much beyond the topic, people have different interests and projects and perspectives. And so I love to get those questions that really reflect where people's experiences are. And so one gentleman asked, he said, he's involved in the nanomaterial side of the technology space. And he said, in his perception, nanomaterials as a buzzword is not quite as catchy or not quite as out there and common as maybe it was 5 or certainly 10 years ago. Is that because that's becoming passé and not interesting or moving away from that? And I said, no, absolutely not at all. It's the opposite. It is this phenomenon of it's becoming so normal that it's not so catchy to call it out as itself anymore. It's just becoming how things are done and manifesting in so many different kinds of ways. And that's a sign of when we think about this hype cycle, which is I think mostly accurate, but doesn't necessarily reflect everything. But you have this sort of early buzz and then this trough of disillusionment, and then it incrementally the use starts to grow back up again. And for your readers and watchers and listeners, that's something to look at if you're not familiar with. It's a helpful sort of image to understand about tech and adoption. But nanomaterials for sure is growing back up, and it's just become a thing. And I think printed and flexible electronics will grow up and not be quite so unique in and of itself, but will just be a normal part of how things are done. And there will still be innovation, and there will still be a lot of opportunities to do new and clever things, but not necessarily on its own as an interesting piece. I think it's just going to become more of how things are done.
Wow, I love that so much, and that I'm so excited to see what this field turns out to be and all the applications it can make an impact in. And I like the part about like kind of the adoption, the S adoption curve and everything like that. So I know we've discussed a wide range of uses in many different fields for flexible electronics. And so for our MSE listeners, specifically students, early career professionals, what would you recommend students that are interested in contributing to this field? What advice would you have for them in terms of next steps or actionable steps that they can take right now to make an impact in the future?
One of the things that is fun about being in a deep tech space and an early frontier tech is that a lot of the work that we're doing has never been done before. So it's completely unreasonable for us to expect to hire somebody that's got 3 or 5 or 20 years of nanomaterial electronics integration, right? Some people have that. Most people don't have that. That doesn't mean that they're not, right? So my guidance to students And I speak with high school groups as well. I'm involved in the STEM advisory group at one of the high schools here, actually, in the Austin area. And it's great to work with the faculty and some of the students on that. But it's to pay attention to the science, really understand and get your basics in place. And understand that the chemistry and the physics and the material science, all of that really does matter. It doesn't necessarily seem super interesting at the time, but take note of that. And the good news is that there is so much work in the universities now, even at an undergraduate level. Most universities and researchers, faculty researchers, really welcome undergraduate support and interest. And so I encourage students at any age to look and see what they can get involved in at universities, at companies. Sometimes it's harder with companies, but often with universities it's a little bit easier because it's still in that educational cultural environment. And to be open to where your interests take you. But there's so much work going on from a materials perspective right now. 2D materials is a super hot topic. And I know that there's a lot of work in looking at how 2D materials can be applied into a range of applications, from biotech to different kinds of electronics. There's a pretty big exploration of materials right now, going back to the semiconductor topic from early on, coming full circle on that, looking at photonics and how does traditional semiconductor materials technology around moving electrons and manipulating and being very clever in electron management, right? Corralling those little guys to move them where you want to, because they get pretty ornery and hard to manage sometimes. But with light, and how do you integrate light and electrons and materials? And that's a whole thing. And there's a lot of really cool work that's going on around that. Also, quantum computing is a super hot topic. And so not just the algorithm side of quantum computing and the logic and philosophy side of quantum computing around, well, what does a computational solution look like that's not just ones and zeros, but it's statistically developed at that point? And what does that look like? But also the materials around implementing hardware solutions for that is so up in the air. There's obviously some notions and some early work that's gone on with that. And there's so much opportunity potential around that. And then pick the convergence of any of those topics. Traditional semiconductor materials with photonics plus quantum statistical computing, right? So or add in the biotech piece of that, right? So all of these pieces, it's so overwhelming, and there's so much opportunity on the hardware side and how these pieces intersect. Just follow things that are interesting to you. Get your science, get your physics. It can go in so many different directions. There's so many questions that can be answered and addressed. And that's really, I think, an exciting thing about being a student right now is technology is not getting more limited. It's just getting more unlimited as we go.
I love that. And that's cool to talk about too, or you talked about like flexible electronics, quantum computing as frontier technologies, but imagine even operating at the intersection between the two, what you can accomplish there. So really loved all of that advice and really enjoyed this episode. Stan, thank you so much for joining us today. It was a blast.
Oh, I have fun talking and thinking about it, and it's great to see you all again, and look forward to talking again.
Absolutely.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.